Let me first do the limits. The simulation or illustration of limits of sequences of functions in terms of limits of sequences is what it was about, and which just didn't work out with the new version of Excel. But I fixed it a little bit, so I think it looks way better. So, so once again, let me just repeat what I told you last time. Starting with a sequence on the x-axis, you can see it in green, right, on the x-axis. So that's the starting point. You can see how they're accumulating x's towards 0. Okay, then we find we go up from each of these points. We go up until we hit the graph. That creates those orange points. The graph is purple, and those points are orange. And as always, we use the graph to find y's. Now we go horizontally until we hit the y-axis, and that creates those blue points on the y-axis. And then behavior of then the sequence on the x-axis produces a sequence on the y-axis. Okay. So once again, if you can try to imagine how. Well, that certainly point is clear. Meaning of that point is it goes up there, the orange point here, and then it ends up with a point on the y-axis. Okay, so that has done infinitely many times, and that's how we got a new sequence. Okay, so all it's done here. It is all done numerically, even though we will do a lot of that algebraically as well. Okay, and then the good news then is what we're looking at here, or looking for here, is the convergence of the new sequence. We start with a convergent sequence on the x-axis, and then we ask ourselves, what about the y-axis? Will it also converge? And it better. If it does, we have the limit exists. If we can carry this out for every imaginable sequence, then we conclude that our function has a limit. Okay, so once again, the definition, that's, well, this is what I just said, but there's a definition somewhere. Yeah, there's a definition, so it has to happen to every sequence. Okay, so if one sequence doesn't work out, which is what we talked about at the very end yesterday, then there is no limit. Okay, so the example of this example of divergence. So the construction is the same. You start with the x-axis again. You see the green points. You progress from right to left. Once again, you find the orange points on the graph. Then based on those, go horizontally, find the points on the x-axis, and you see how it is going in the vertical direction. The arrows have disappeared, unfortunately. Yeah, so I used to have arrows, and now they're gone. Anyway, so then we have divergence. So that sequence, the blue sequence on the y-axis, diverges, so that's why there is no limit of the function. The function being the graph of which is the purple one. Even worst case scenario is this, and that is with the one with the wild behavior, infinitely many times oscillating graph of the function. As you can see, what's happened to y's, what we discovered yesterday is that they fell, not literally, but fell the whole segment between -1 and 1. Okay, but otherwise it's very similar. You don't see arrows here because there used to be arrows. Oh, there. Oh. No, there are no arrows. So definitely I added arrows here, and then they don't show. Well, there is. I think I can see one arrow. You can see at the very top, the blue one has an arrow there. The rest of them have disappeared. They're a different version of Excel again. Anyway, so that's how we do it. The last topic, once again, is an exception of oscillation that is, well, next to last, this one, that the sequence might converge. Doesn't mean that the limit exists, because you have to demonstrate that happening to every single point. Okay, and this example will skip. And now the next topic is one-sided limits. So the functions have much more stuff going on in comparison to sequences. So that's why we have to check out infinite many sequences in order to determine the behavior of the function at one single point. And then there are also, as I said, one-sided limits, which is what we just saw, and that is the idea being to ignore half of the function. So it is still, again, we are interested in what is happening with y equal f of x when x approaches some value of a. Okay, so but that's the original question. Okay, so new question is the same question. X approaches a from the right, which is what all the pictures that we have seen are. X was approaching a from the right. So this is the sequence from the right. But implicitly, we also we're thinking about sequences that approach it from the left, like this. So it's also xn, and both of these sequences all possible sequences have to produce convergent behavior on the y-axis. Okay, so but sometimes functions are defined on half of the well, we can let me go back to this function, which, as you might remember, for a while, that that limit. So this is the sine function, sine x. If this is being 0, okay, let me. So this is my graph. So you might remember that if you start with a sequence on the x-axis like this, 1 over n, so 1 over n, f of 1 over n is equal to 1, and therefore the limit is 1. But f of negative 1 over n is negative 1, so then it converges to negative 1. So the behaviors on the left and on the right are different, and that's why we are negative 1 over n, that's why there is no limit. Okay, so remember all the sequence converge to the same number. That's a requirement for the limit. So that's the negative conclusion, sort of no limit. But look at it. If we ignore half, if we only take half of the graph of the function, and we do, as I put it over here, only concentrate on the function f values of x to the right of 0, then everything is fine. Everything is fine because this is what's left. I literally take the graph that I already have and just erase half of it. So that's what I'm left with is this. Okay, so then there is no issue of what's going on to the left of 0. We have to consider sequences to the right of it. So let me just define it, what we're talking about here. So definition, the limit of y equal f of x from the right, I'm sorry, at x equal a from the right is equal to L if for any sequence xn with xn converges to a and xn larger than or equal to a, so strictly larger than a, we have the same conclusion. So f of xn converging to L as n goes to infinity. Okay, so that is the definition, limit of a function at a point from the right. Okay, at a point. Okay, so that's exactly what is written on the right, and this is the one extra condition that we add. So one extra condition actually weakens the requirement on the function. So if we consider only half of the function, then the fewer things can go wrong. Okay, that's example of the sine function on the right shows exactly why this is the case. So similarly, the limit from the left, the limit of y equal f of x at x equal a from the left is equal to L. So it's the same story. We certainly don't expect this thing to look very, very different. We only look at the sequence that is from the left. The sequence xn converges to a from the left, meaning that all of these numbers are smaller. Okay, it's working. If, let me just repeat it, for any sequence xn with xn converges to a and xn less than a, we have, same as before, f of xn converging to L as n goes to infinity. Okay, so that's the differences here. On the right or on the left. Okay, so this is the second situation. We're looking at what's going on the left, and meaning that we erase half of the graph of our graph of a function, and we concentrate on this orange part. And as you can see, there is no jump as we're approaching 0 from the left or from the right separately. As long as it's separate, there is no jump. The behavior is not only very steady; it is in fact constant. So there is no change in y. So based on this, well, let me write the notation first. So notation is a limit f of x goes to a plus. So the little plus is put on the as a superscript. So it is if x is close to a but larger than a. Alternatively, a minus. That is from the left. So right, left. They also called one-sided limits. Okay, there is a, let me separate this. Another way to put it is f of x. Well, you know how we can break it. F of x goes to L as x goes to a plus, and f of x goes to L as x goes to a minus. So that's alternative way to put it. And there's another way is wherever you have x goes to a plus can be replaced with a like this, like this. I think this is kind of a revealing of what's going on like this. Okay, so as you can see, the arrow is going down as if we're talking about something decreasing towards a. So x decreasing towards a. I sometimes like the notation on the right, but the one on the left is actually more common. Still worth mentioning. Okay, so the second one on the left, it's like this one is x-axis. What do we know? What does the x-axis looks like? It looks like horizontal. It is a horizontal line. Okay, so okay, that makes sense then to talk about left and right. On the other hand, does it really have to be x-axis? Does it have to be horizontal? Generally, it doesn't have to be. So in that case, we can speak of increasing, decreasing behavior, and this is what the second version of this notation suggests. So then the limit of sine x x goes to 0 plus is equal to 1, and limit sine x goes to negative 0 minus is equal to negative 1. Okay, so those are the conclusions based on the picture that we have here, or based on the computations that we have had. The behavior is fairly transparent. So you certainly can think of examples that are nastier than that, and then you'd have to be more careful. But frequently, what you might be facing is something like that. And you might be asked to discuss limits just based on this picture, which is with nothing but the graphs. You might be asked to discuss the limits at every point. And kind of vaguely put, but the limits, meaning that why is it plural? Because it's limit. There's a two-sided limit one started with, then there's a left-sided, and then there is a right-sided. So there might be an idea of you might be asked to then sort of to know what the answer is supposed to be. Okay, so let's quickly run through this. First of all, the one thing to note is when there is a graph of the function looks like a rope uncut in continuous, there is nothing special about it as far as limits. So there's only two suspicious points, and that is x equal 1, x equal 2, and if we take them out of consideration for a moment. So for x not equal, or a rather, a not equal to 1, a not equal to 2, a limit f of x goes to a exists, and equal to, what is it equal to? No, infinity. So let me pick a point, say this is the point I'm talking about, and as you can see there is nothing special. So once again, imagine zooming in on this point on the graph. So we are approaching a on the x-axis. Remember that there are these pictures. Okay, so well this one, in fact. So we have these green dots on the x-axis, and then we'll produce blue points on the y-axis. So let me carry that out. So, well, these are the x's. Okay, then I have points in, say, orange on the graph, and then I have, say, maybe in black, some y values. Okay, so here I'm moving right to left. Here I'm moving down like this. And then on the x-axis I'm doing that. Okay, so I imagine that at the end of the arrow there is accumulation of those points. That's what we're talking about convergence. So I have once again here I have xn, a sequence that converges to this number a, and the question is what has happened to f of xn. So and the answer is this. What is the importance of this point? This is where the sequence of yn, this is yn, right? Where it converges. So what's the importance of what is that point, if you can tell? Well, it is the limit. The arrow is the limit, but there is actually a specific answer here. Look at those, yeah? The vertical line followed by a horizontal line. What's the importance of that? So I'm talking about what is the relation between A that you can see and this and this. look carefully at the graph. What is the meaning of this point? It is the y value of
point on the y-axis and then.
yeah. So can you then say what should I write here? So or over here. Well, what am I writing here? So I want to write specifically what that value of y is. What is it? Well, let me maybe like this. Okay, so these are the x's. Okay, so once again, the meaning of this point on the y-axis. There are no limits. Forget about the limits. There's an x value over here, and there's a y value over there. They are related to each other somehow. Well, if you have any idea, it's not meant to be complicated. It takes you back a little bit, and it seems you've forgotten. You don't recognize something that is meant to be familiar. There is nothing but the graph of the function, a point on the x-axis, value of x, and there's a corresponding values of value of y, 1, value of y, and you can just write what it is equal to. Yeah? Where the relation between x's and y's, where does it come from?
Input and output.
Yeah, so that's right. So x equal a is the input, and that one is the output. What's the output? What? Yes. That's all. Yeah, it was meant to be complicated. It's just sometimes hard to recognize something familiar, especially you shift. Things are happening to the right, to the left of the y-axis, and that might be a little bit unfamiliar. So this is f of a then, and that is the conclusion of that. That's the answer to our question, that the every limit other than possibly those 2 points exists and equal to the value of the function at that point, which we have talked about that just a bit. We'll talk more about it. It's called continuity. And indeed, if you look at every point on the graph except for those 2, the graph looks very nice. It looks like a continuous piece of a rope. Okay, so and once again the limit is y, because the limit is equal to f of a. The limit of the function is equal to the value of the function. Okay, that's what we're saying over here. Okay, so that's the simplest outcome. It is the outcome that is to be expected. Everything else, for the most part, is what we're trying to avoid, because those functions are those or locations where the function misbehaves. Okay, so we just to classify that situation, we'll look carefully at those behaviors, and then that's why we want to look at the one-sided limits. So if we take first a equal 1, okay, so in other words, I'm talking about this point. So as you can see, there's only one value of the function at that point. It is right here. In fact, it's probably equal to this value. But because there are those little circles indicate that the graph is missing the end on both of those 2 branches. So okay, so what is the limit f of x? X approaches rather 1 from the left. Subscript minus. Okay, so what do we get? So remember, we are throwing out the whole graph pretty much. Okay, in like this manner. So for the moment, for this computation, we only look at x's less than 1, which means that this branch is gone. Okay, so what's the answer?
Three.
Yes, the answer is 3. Okay, so if we only looking at this branch separately, the answer is 3. Why? Because that's where, this is where things are happening, this is where they're happening. Okay, so the rest of the, neither that point in the middle nor the branch to the right contribute anything to the behavior of the function that we're concerned with. So that's why the answer is 3. In the meantime, if we look at it from the right, x approaching 1 with plus f of x, we are doing the different. We are now looking at the behavior of the function. This part of the graph, the only part of the graph that matters. Okay, so then the answer is
-1.
-1. Okay, the conclusion is as before. Well, the conclusion is for 1, then the well, the number 1 conclusion is that limit x approaching 1, f of x, well, that's not really a conclusion, but let's say it's an observation that about the limit, as you can see, there's neither plus nor minus, which means that we are allowed to approach this time 1 from both left and right simultaneously or alternatively. So what is the conclusion?
Does not exist.
It does not exist. Okay, great. So it does not exist because there will be 2 patterns of behavior, one approaching 1, the other one, a -1, the other approaching 3. So that means that there is no limit. And the actual conclusion that I want to make here is y equal f of x is discontinuous at x equal 1. Okay? We can see it, but we want to put it in a more precise terms, and that's why we're doing limits here. So a equal to 2 is the other problem. Okay, so look carefully at the picture, and once again we're looking at the limit from the left and from the right. Okay, so this is the point. What are the limits from the left and from the right? At 2?
Point something. 2.
Yeah, it looks like this is the important point, so maybe 2.5 or something like that. Okay, so in fact it is the same for both of them, right? And in fact, the two-sided limit is 2.5 as well. So x approaches 1 for both sides. It's still 2.5 because it turns out to be the way it works out is the same on both sides. So, but the conclusion, however, which is not based on this, but rather the behavior seems to be very regular for from both directions. Unfortunately, as you can see, there is a hole in the graph. The function is simply undefined, at x equal 1. That was supposed to be 2, I'm sorry. At x equal 2. So once again, y equal f of x is discontinuous at that point. Okay, so what discontinuity with that might come from? A variety of things. Limit from the right does not match limit from the left, or when they do match, maybe the function is undefined. Thirdly, in fact, if it is even defined, it might be defined at some different point. So that's just different ways to see the problem. So hypothetically, I could add an extra point over here and say, well, like this. Okay, so if this point, that blue point at the top, is the value of the function, then even though the behavior from the left, from the right is good, and they match each other, there's a missing point in the middle, and that's why you have to still conclude that the function is still discontinuous. So that is the how in a more precise way, without referring to pictures, we can study limits of functions at points, as well as continuity of functions at points. And its primary tool is the one-sided limits. They are studied, of course, with primarily the limits. Okay, the limits of sequences. Okay, so that's how we define it, and that's how we can continue doing it. So we'll revisit this a bit later, one-sided limits, so we have defined them, but the continuity we'll review later on. I want to move on to the algebra of limits. The algebra of limits, that since limits of functions, okay? Just recall the short list of limits of sequences, and then everything matches. So once you understand sequences, limits of sequences, you can understand functions as well. So an converges to a, bn converges to b, and then we have the sum rule, an plus bn converges to a plus b, and then we have the product rule, an times bn converges to a times b. Constant multiple rule is can converges to c times a. C is real, any real number. And finally, the quotient rule, an divided by bn is going to converges to a over b as long as b is not equal to 0. Okay, so that the expression makes sense. So this is familiar stuff about sequences of limits of sequences, and now we have the same or similar or matching property of limits of functions. Okay, so once again it will be 4. So the sum rule, I want to use the arrows again. Sum rule. So well, there is still a build-up. Okay, so this is one theorem, with this being the build-up, and then what follows is the punchline. And similarly, we also have to start with specifying that the limit exists in the first place. So f of x goes to f capital, and g of x goes to g capital. Okay, and as x approaches a, or x approaches a minus, x approaches a plus. So all the three possibilities we take care of, because we have right now 3 types of limits of functions. So two-sided and one-sided. Okay, so all the formulas will be applicable to each of the 3. Okay, and then we conclude once again the sum rule. Everything is just almost exact match. The notation slightly is different. So the sum rule is f of x plus g of x. Just as we have algebra of limits, just as we have the algebra of sequences, we can add them one by one. We can add functions. Okay, so maybe that is worth reviewing, but let's first write this up. So it's f plus g. Constant multiple rule is c f of x. Limit is cf, c real. The product rule is f of x times g of x goes towards f times g. And finally, the quotient rule is f of x over g of x goes towards f over g. as long as g is not equal to 0. Okay, so so first of all, about the algebra of functions. So you can see here right away the four main operations. I didn't put subtraction here, but certainly you can think of that. Certainly now no trouble to put a minus here, and that works out exactly the same. That would constitute the difference rule. But anyway, so these are the four main operations on functions. They come from the main operations on numbers, right? So in other words, since the output of a function is a number, so whatever you do with the output produces new functions. So in this particular case, two functions have two outputs, and then if you add those outputs together, the end result is a new function. So just as a review, so if this is f, x comes in, y comes out, and this is g, x comes in, y comes out. Okay, so they seemingly exist apart from each other, but then what we could do is we could create a new function like this. A new function that takes x in and takes out, I don't know, this is say y1 and y2, and this is y1 plus y2, and that, how about z? Okay, so that's a new function, the sum of the two. So you take x, plug it into this black box. Inside of what's happening inside of the black box, we know for a change, because we copy x and plug it into f, and the same copy plug it into g. Okay, then the outputs are added together, and that's the output of the new function. Okay, so the input is x as before, and this is the output. Okay, so that's how diagrammatically you add functions, but you certainly can easily think of how to represent algebraically, or how you see additional functions done with algebra. So one function is x squared, the second function is cubed. You can look at them separately. If you put a plus between them, you have a new function. Okay, you certainly can multiply if you like, or divide. Okay, so all of these functions make sense, even though there is a chance that with this you end up with 0, but it only means that the domain will have to be taken care of. So x equal to 0 is not within the domain, but other than that, there is no problem of doing any operations with functions. Okay. Okay, so and then we can do the operations with functions. Then turns out that just as with sequences, limits behave well, predictably, and really, if you try to guess what the answer is, the answer is that. Okay, so addition of limits produces addition of addition of functions produces addition of limits. Okay, that's the sum rule. Multiplication of functions produces produces multiplication of limits. So everything is predictable as long as so I won't forget to repeat this as many times as it takes. You have to draw these conclusions. You have to assume that there is limit in the first place for those two functions, because so when there are three functions, then you have to start with the function having limits before you can conclude anything about the new function built from the two old ones. Okay, so yeah.
Those capital letters just mean like the limit of function f and the limit of function g.
Right. Yeah. So it's a number, and I'm just choosing the letters that match the function, so that there's some kind of a clue as to where f came from. Okay. So then like I had, you remember, an goes to a over here. So this, in a similar fashion here, I chose limits to be equal to a and b, even though it is, you like to call it L because L stands for a limit, but if you have more than one function or more than one sequence, then it is better some kind of matching. There's some kind of matching letters that's suggestive, suggests what's going on. Okay, so so the computing is no trouble using these properties. I don't want to do a lot of it relative to what we did with the limits of functions. The properties are not any challenge to remember, but let me carry it out at least once. as an example. So I have f of x equal to, I don't know, 2x cubed minus 3x squared plus 5x minus 1. Okay, so suppose this is a polynomial, and as you can see, the operations involved are very simple. They are addition, subtraction, and multiplication. You start with certainly taking care of these two functions that are not x squared and x cubed, and you want to know what's happening with those before you proceed. So the question might be evaluate a limit f of x as x goes to, say, 1. Okay, so so what you identify the parts that need to be taken care of ahead of time. So I need the limit of x cubed, x goes to 1, and limit x squared, x goes to 1. I'll start from the right. Why? Because I want to break it apart. X squared, I'll break it into 2. There's a limit of x times x. Okay, and what I know about this is that limits, the function is really very simple. These two, x and x, both of the limits exist, and they equal to 1. So, well, there we go. I'm applying the product rule right away, and I have limit of x times limit of x, which is 1 times 1, which is 1. Okay, so that's the limit of x squared as x approaches 1. From that, I could proceed and find the limit of x cubed. How? How do I find the limit of x cubed?
Would it be the same way, except x times x times x?
I could. You definitely could. I was thinking that you break it into 2, so I could apply the product rule. I could break it into x squared and x. We just taken care of x squared, right? So we already know its limit. So how about this? There's a limit of x squared times x. Okay, and we already know that the limits exist for both. Okay, so if both of them exist, then the product rule applies, and I have limit of x squared times limit of x. X goes to 1, and I know that limit of x squared is equal to 1, limit of x is also equal to 1, so the answer is 1 again. Okay, so that is the preliminary computations that we had to take care of. And now we're putting everything together. Those circled, the green functions are now known. Their limits are 1 and 1. And all that's left is just to apply, well you'll tell me. So I'm evaluating a limit fx. X goes to 1, which is 2x cubed minus 3x squared plus 5x minus 1. What is the first rule I apply?
The product rule.
No, well, there's really no product here to begin with, but secondly, remember the rule we talked about, the idea we talked about recently when we talked about limits of sequences. The last operation is used first. So the last operation is, these are the last operations: subtraction, addition, and subtraction. So these are last operations, and they are taken care of first. If you're doing it this way, you could actually reverse it in the whole the whole thing eventually. But if you are doing computation like one line computation, which is what I started, then yeah, the last operation is used in order to do what? To use the sum rule in this particular case and break your limit into 4 simpler limits. Okay, so that way you know where you're heading. So you have a limit of 2x cubed, and then you have a limit of 3x squared, and you have a limit 5x, and you have a limit of 1. Okay? That is the sum rule. The last operation is addition subtraction, so I could use the sum rule, difference rule, and then I have, instead of having one big limit, I have 4 smaller limits. Okay, and now, okay, what's the next rule? I look at what is the last operation in each of these limits. So 2x cubed, what's the last operation? Multiplication, indeed, and not just any, it's multiplication by constant. So we're applying the constant multiple rule. Okay, how? We just, it looks very simple, but that maybe is not, it is more compact, but not good for algebra, but actually true, under the constant multiple rule, the constant gets out of the limit, so this is what's happening. Okay, so 2 is taken out. And then what remains is just the limit of what's left, x cubed. Similarly, 3 gets out, x squared. And 5, limit x. And the last one, I'm not going to spend too much time. I know that the limit of a constant function is that constant. Okay, so it's not going anywhere. So and then we just use those these limits we just found, these two limits we found. So both of them are equal to 1. We substitute, and we have 2 times 1 minus 3 times 1 plus 5 times 1 minus 1. 2 minus 3 plus 5 minus 1. What is it? 3? Right? Okay, so so this is the basic task that you might be asked to do when you compute a limit. Okay, so so like always with algebra, it always you do it easily once, you do it a few times. So but otherwise there's no you just follow the rules, just like with limits of sequences or any kind of algebra of numbers that you saw previously, and then you follow the rules, and the rules are spelled out. So these are the rules. There's a really short list of rules. Right here you have 4 rules. Every time you ask yourself which rule to apply in the right order, just like the order of operations, only in reverse. And then you'll be very comfortable if you just do it a few times. The mistakes usually comes from just careless application of the rules, or just forgetting the rules. And let me see what can possibly in this computation, what could go wrong. Not really much that can go wrong here, because this is just one way of doing it. There are certainly a few others. So in other ways to go in the opposite direction, which is rather than unwrap the function and looking at the last operation of that function, you can start with the smallest pieces that you can recognize, and then build up. So you rather than having one line of a computation, which might be cumbersome and kind of intimidating, instead you could just look at it the way I started, in fact. So for example, I started with 2x cubed over here. No, I'm sorry, I started with x cubed, I found the limit, then I evaluate the limit of 2x cubed, and then I evaluate negative 3x squared, and then 5x, and then 1, and then put them together. Of course the answer is the same, the amount of work is exactly the same, the point of view is slightly different, but it's just fine. Find out which way you find the most comfortable. So as I said, it is very typically what you ask to do in a test in your online homework is compute a limit. However, by its nature, it's algebra, so it really does not call for any deep conceptual insight. Okay, so it is just following the rules, and unfortunately the problems like that are prominent because they're so easy to test for. Okay, it's like asking a person to, instead of writing an essay, just making sure asking a person to write an essay and then grade it entirely based on spelling. Okay, so the concept, whatever the ideas are behind, is really not important because you have to think about it. It's very hard to actually evaluate. I don't know how they do it in like English composition, but it's the same problem in mathematics. So how do you evaluate the understanding of ideas? And the answer is, well, unfortunately, you often are limited to problems that are computational, because at the end you can test, well, if you say the answer is 4, I know you're wrong. Okay, so there, you failed. Okay, so none of these problems are especially important, but they are easy to test for, and that's why they are common. Okay, so that is an unfortunate reality. So then these problems will appear. I will not overemphasize them, but they will certainly appear, and in this course and in the following. Okay, so so the practicing with these problems is probably a good idea. You can do some reading, or either online or test or the upcoming homework. The textbook, if anything, the textbook contains a bunch of problems of this nature, and we might do some more examples later on. But I want to look at what we actually faced elsewhere, the really tougher problem, still computational but tougher, and that is all kind of indeterminate expressions. And you face the same thing here, indeterminate expressions. So what about infinities, and what about division by zero? So these are the problems that we already faced with sequences. So here's an example. Well, this one is simple. X goes to 1, and x plus 1 over x minus 1. So first of all, you're supposed to evaluate the number one conclusion that you should make is that there is a last operation is division, which means that it might be calling for what's called to be used here is the quotient rule. Okay, then you go back to the quotient rule. What do you see? The requirements for the quotient rule is right here. The limit of the denominator cannot be equal to 0 if for this thing to work out. So unfortunately, it is exactly the same. The limit x minus 1 is equal to 0 as x goes to 1. Okay, so no, quotient rule does not apply. Okay. So that's one situation you might be facing, and then you should be able to draw conclusions based on other patterns of behavior. So what we have seen with sequences. So what's happening is that the limit of the denominator is going to 0. The limit, then what we proceed is explore further. We look at the limit of the numerator, and the limit of the numerator is what? 2. Okay, so the denominator goes to 0, the numerator goes to 2. What would you guess the answer is? The limit, the original limit. This one goes to 2, this one goes to 0. Well, if they were sequences, you probably wouldn't hesitate. The numerator goes to 0, numerator goes to 2, denominator goes to 0. Where does the whole thing go?
1.
No. You divide by a number that is small and small and small and small.
It goes to 0.
No.
It does not exist. Or 2. All the above.
Well, okay, take a minute. I think you mentioned every single possibility except for the one.
Well, those have been the choices as well.
X plus 1, what if I put this way? Is this easier? The numerator is not going anywhere. It is 1. The denominator is going to 0. Where does this whole thing go? Infinity, right. So this one goes to infinity, and that one also goes to infinity. Okay, so when the numerator converges to a number that is not 0, but denominator is going to 0, then you divide a number that is kind of a stable divide by number that is small and small and small, which makes the whole thing larger and larger and larger. Okay, so there you go. You have infinity. Unfortunately, that's not the answer, and I'm not sure if you see why this is not the answer.
Is it because x is only going to 1?
What?
Is it because x only goes to 1?
No. What's wrong with that?
It can't be infinity if x only goes to 1.
No. You see, this it could be. Remember the example we just saw right here. 1 over x. See, the x going towards 0. Okay, and in the meantime, y goes to infinity. Okay, so it could go to infinity. The question is exactly what the function 1 over x has. The problem this function has is that there are two infinities. It is really never the answer is infinity. It is always either one or the other. Okay, and it is actually matters here. We can figure it out because the graph roughly looks like this. So like this. Like this. So for as long as x is larger than no, I don't think I did it right. This is it has a hole. The function is undefined at 1. So this is 1, and then where the function is undefined, and this is what roughly the graph looks like. And you can see the behavior of the function here as it going towards 1. And let me just write the answer based on the picture without going into computations. 1 plus x plus 1, x minus 1. Okay, it is plus infinity. This is what I'm talking about. And then for the behavior on the left, x plus 1, x minus 1 is equal to minus infinity. Okay, so that is reflected in the graph. If you think about it, whenever think about, if we're talking about x plus 1, while x is close to 1, the whole thing is close to 2. So this one is roughly 2, and the numerator is roughly 2. Okay, so even if it's not exactly 2, it certainly is positive. In the meantime, the denominator is different whether we are to the left of 1 or to the right of 1. So x minus 1 will be x plus 1 over here is positive. That's why the whole thing goes to positive infinity. To the left, x minus 1 is negative. Why is it plus? It's minus over here. Okay, it's negative, and that's why the whole thing goes to negative infinity. Okay, so it's all the sign of the function determines which infinity it is. We know that it is infinity, we just don't know which one. Okay, so we determine that it plus or minus. So I put a plus minus here, even though it's an incomplete answer, but at least it's not incorrect. And then we determine which one which, and this is the answer. Okay, so that is not the worst case scenario, though. That is what we have seen. This is x squared minus 1 over x minus 1. And x goes to 1 again. So, once again, quotient rule, no, because the denominator is the same, so limit of x minus 1 is 0, so that quotient rule does not apply. But the what makes it worse is the limit of the denominator. I'm sorry, of the numerator. The limit of the numerator, what's the limit of the numerator? What's the limit of the numerator? 0. Okay, so in other words, what we end up with is an indeterminate expression. And what's the plan for those? For indeterminate expressions, what do we do with them? What did we do? Why I'm asking, because we had this situation with sequences. We had an indeterminate expressions, and what was the plan, if you remember? Well, is 0 over 0 the answer? No, so that's not an answer. So how do we find the answer? Or what is the answer, if you can see it?
You break apart x squared
Right,
minus 1.
right. So the answer is algebra. the expression that we have is unfortunately fails to be evaluated in a simple manner as I have done just a few times. So the answer is algebra. In this particular case, turns out that we can factor the numerator. In this particular case, we factor the numerator. So my limit becomes x squared minus 1, x squared plus 1, x minus 1. X goes to 1. At this time, what I do is I cancel x minus 1 naturally. So what justifies canceling x minus 1 is a simple fact. You know, canceling you have to be careful about canceling because you're dividing, and when you divide by something, there's a chance that you're dividing by 0. So dividing, the canceling it here is by means of dividing. I'm dividing numerator by x minus 1, and I divide denominator by the x minus 1 expression. Okay, so it means that we have a division by expression, and that expression has an x in it, which means that it's potentially is 0, and no matter what, division by 0 is not allowed. So certainly not an algebraic operation. Okay, so fortunately it's only equal to 0. X minus 1 is equal to 0 only if x is equal to 1. And that is exactly the point that we are not concerned with. Remember, we evaluate the limit of a function when what value is ignored is that point itself. So the limit of a sequence, remember we have a sequence converging towards xn converges. This is the picture. No, that's not the picture. This is the picture. Look at the green sequence. It converges towards 0, but it's never equal to 0. Okay, so even though there is a chance there that the function itself is undefined at that point, that's okay because we are staying away from that particular location, and everything works out just as it works out here. We divide by x minus 1, which is never equal to 0 as far as the limit is concerned. And it works out very nicely because we end up with x plus 1, and the limit is 1 plus 1 is equal to 2. Okay, so that's how we handle indeterminate expressions that could be of different nature. Remember that what we saw with sequences, it was not only 0 over 0, it was infinity over infinity, it was infinity minus infinity. Expressions like that were to be handled by means of modifying the expression itself in order to apply some different rule from the one that failed. So quotient rule failed, even though it's really not the quotient rule that failed, we failed. But we were able to avoid, as you can see, at no point we use the quotient rule anymore. We cancel x minus 1, and then computations become straightforward. So next time we'll talk about how to deal with infinities and in more indeterminate expressions. Okay? All right.